step 2 practice. We're going to be working on example 2 in this video, which is a parallel circuit. So just like before here, we're going to run through and we are going to determine the math first, and then we're going to figure out the screen capture afterwards. Okay, so your assignment is going to look more like this, but I'm going to be writing it out here. So again, we need to start figuring out our known information, all right? So we have Ohm's law, which is E over I times R. We have power, which is equal to current times voltage. And in this case, we're going to need 1 over resistance total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And we're also going to need to know Kirchhoff's law, which states that in parallel, our voltage is constant and our current, it changes, adds up. All right. So we know that the voltage for this whole system is 9 volts, which again we know according to Kirchhoff's law that every single component is getting like a plus 9 volt on this bar, a 0 volt on this bar, so that's always a potential difference of 9 volts. We don't know our current yet, we don't know our resistance total yet, we don't know our power total yet. So I'm going to do my resistance total, which is 1 divided by 2,200 plus 1 divided by 4,700 plus 1 divided by 10,000. Okay, and again, I'm not done with that calculation yet. I need to hit x to the negative 1, which tells me that my total resistance is equal to 1.3 kilo ohms. All right, so 1.3 kilo ohms. So at this point, I can use Ohm's law, E over I times R. Once again, we're coming up with I. So it's going to be 9 divided by 1,300, which is equal to 6.9 milliamps. Okay, now we can take that number 2 and we can multiply that by 9, which is pi p is equal to I times E. And that tells us that our power here is going to be equal to 62.3 milliwatts. Okay, so that's the power that's going to be consumed here. So over here, we do know what our resistors are equal to. This is equal to 2.2K. This is equal to 4.7K. This is equal to 10K. So again, coming up with I for these is pretty easy. You can say 9 divided by 2,200 is equal to 4.1 milliamps. 9 divided by 4,700 is equal to 1.9 milliamps. And 9 divided by 10,000 should be 900 microamps, right? Because I go 1, 2, 3, that's not enough, so now I need to go 1, 2, 3. So I add 2 zeros, then it goes milli to micro. So again, we can take that number, 900 microamps or whatever these amperages are, and once again we can say P is equal to I, which in this case is 9, and it will be across the board, 9 times 0.0009. All right, which you can't see, it's this number times 9. So in this case here, this is 8.1 milliwatts. 9 times 0.0019 is equal to 17.1 milliwatts. And then the smallest resistor, so the path of least resistance, should have and does have the most amperage, so it's also going to have the most power, right? It's going to consume the most power. 9 times 0.0041 is equal to 36.9 milliamps, right? So 36.9 plus 17.1 plus 8.1, all of these are the same, like units, so I can just add them up straight. It's equal to 62.1 watts, not amps, milliwatts. So once again, here my answer is 62.3. I'm off by 0.2 of a milliwatt. So 2/10,000ths of a watt. It's a different number, but the same value, basically. Okay, so that's good there. So now we're going to move on to the screen capture, which going through this process in TinkerCAD is a little bit more complicated than the series circuit example. So let's get to that right now. Hey, what's up, everybody? So yesterday during class, I realized that there's an easier way to set up circuits. So I'm re-recording the second half of this lesson to reflect the easier way to do it. Another thing I just want to talk about quickly within here is how to calculate for power again. And then we're going to move into TinkerCAD. So if you've already done your power stuff, you can just skip over to the TinkerCAD portion of this. So once again, power is equal to current times voltage. So when we go through, one of the first things that I'm going to start to do here is just start to type in my current. So 6.9 milliamps is equal to 0.0069 amps, and I'm going to multiply that by 9 volts. And that's going to give me 62.1 milliwatts worth of power. Now remember, power total is equal to P1 plus P2 plus P3. So all of these numbers should match. And you can see that I've already erased this because I've already done this, and I actually inputted 900 microamps wrong into my calculator. And because of that, when I added these up, they did not work originally. So once again, this is just a really important lesson that like adding these things up and checking your work is important because anybody can make a mistake on this. So when I go into my next one here, which is going to be 9 times 0.0041, I'm left with 36.9 milliwatts. Now, that's the majority of your wattage, and that is because you have the most amperage in resistor 1 out of all of them. So that totally makes sense. It's the path of lowest resistance, so it's going to have the most electrons running through it, and that's also going to give it the most power. When we come to the next here, we're going to say 9 volts times 0.0019, and that's equal to 17.1 milliwatts. And then lastly, 9 volts times 0.0009, right? Because 900 microamps. So if we go, we need to move it 6 places. 1, 2, 3, 4, 5, 6. That's equal to 0.0009. When I hit enter there, I get 1, 2, 3, 8.1 milliwatts. Okay, so because all of these are the same unit, I can just add them up. 8.1 plus 17.1 plus 36.9 is equal to 62.1 milliwatts. So exactly what we have there. All right, so let's flip over now to, that was power. We're going to flip over now to setting up TinkerCAD. So I've already started this process. When we look back over here, you notice that there should be 1 voltmeter, 3 amp meters, a 2.2, a 4.7, and a 10 kilo ohm resistor. So This is my resistor 1. This is my, which is 2.2. This is my resistor 2, 4.7 kilo ohms, and resistor 3, 10 kilo ohms. I have a voltmeter and 3 ammeters on the bottom, and I already have my 9-volt battery connected to my breadboard. So the thing that I realized yesterday that makes this easier is if we basically assume that this is the negative bus bar on the top and the positive bus bar on the bottom, it's a lot easier to set the circuit up. So if we were just to connect our resistors in parallel like we usually do, there'd be a line that would run down in between here, like a circuit connection, which would give all of our ammeters bad readings, and they'd all read the same value actually. We need them to all be separate. So we need to separate out like each one of these chunks individually. So in order to do that, we're going to use the negative bus bar on the top and the positive bus bar on the bottom. The reason why I'm choosing that is because basically when I rotate these things, positive goes down, negative goes up. So I'm going to set this up, and I prefer that you do too, so that the leftmost resistors are 1, the center resistor is R2, and the rightmost resistor is R3, right? Because we read things from left to right. So that just makes a logical decision. Now, this black bus bar up here is going to supply electrons to each of these 3 resistors here, but they won't do it yet because they don't have power connected up there. So in order to connect the negative bus bar, all we need to do simply is just connect a black wire between these 2 points, and we're going to set that to be black. So now electrons can travel across this wire. They can travel all the way down the bus bar, and they can travel to each one of our circuits here. Now, when we switch back to like the circuit, notice the voltmeter goes from like the negative side to the positive side. So all I'm going to do is here's negative. I'm going to connect that to the negative bus bar. Then here's positive. I'm going to connect that to the positive bus bar. And now if we were to start a simulation, we would read our voltage, but we don't read any amperages, and no power is going through our resistors because there's no positive pull to draw the electrons through these resistors because there's no complete circuit. So we're going to complete our circuit going through our ammeters. So because this is a negative bus bar at the top, we're going to come from here to the negative connection down here. We're going to change that to be black. And then the positive connection is now going to go to the positive bus bar, and we're going to change that to be red. We're going to start the simulation now. We can see the power is going through resistor 1. It's not the right amperage because we've changed our entire formula at this point because total resistance has changed. But at least we can see that there's a complete connection here. Once we connect up the other ones, the numbers will align properly. So now we can connect up here. Okay, so again, I've connected the negative bus bar to here and the positive bus bar to the positive end. And then again, negative to negative. Positive is going to go in the positive bus bar. So now when I start my simulation, we see all of our recorded values. And I'm just going to take a look at my sheet, which I can't really show you both at the same time, but I'm just going to read off what we've calculated. So we calculated that we'd have 9 volts of power. We actually didn't calculate that. We just know it. 8.99 rounds to 9. That's good there. For resistor 1, we have calculated that its current would be 4.1 milliamps. If we were to round this number to the nearest tenth, it would round to 4.1 milliamps as well, so it's exactly the same value. Resistor 2, we have calculated 1.9 milliamps. Here again, if we were to round to the nearest tenth, again, we'd get 1.9 milliamps, so it's exactly the right number. Lastly, we've calculated 900 microamps. This is outputting 899 microamps. So at some point, probably due to rounding, we are seeing a very small error here. We're talking about 1/1,000,000th of an amp. It's simply a rounding error. This is perfectly close enough to be accepted. And again, when we add these things up, it's equal to our total current. So that works for us here. So what we're going to do at this point is we're going to take a snapshot. And remember, we always want to grab all the important information. So like I'm going to include the battery within that. I'm going to include all of my multimeters. I'm going to include my resistors and all my wiring. And then I can drop that information into the slideshow. All right. I hope that helped everybody today because this is the easiest way to set these up. I cannot think of any way that would be simpler, so I would recommend that this is what you find folks go with, and we'll go from there. All right, have a great day. Bye-bye.